All right, so we're talking about determinants. Basically, determinants, let's talk about what are they. Determinants are two matrices as slope is two lines. Okay, so like for example, you look at, a line, that slope, that rise over run, right? The slope tells you how your line changes over time. The rate, the slope is a rate, right? The rate at which your line is changing over time. Okay, y'all follow me on that? Does that make sense? So if your slope is a rate, like for example, like 60 miles per hour, that's a rate, that's a slope. You know, if your slope is a rate, your determinant, or it's a rate of one line, your determinant is a rate of what we call a vector field. So a vector field, if you're not aware, is something with a whole bunch of vectors in it. And we're going to talk about vectors more in the next section. But think about a vector field as something that anything that flows. Like for example, like a river, the current of a river, that's a vector field because it's all flowing in a particular direction. Y'all see what I'm saying? So this could be the current of a river. This could represent the current of a river. If I drop an object in it, like a pebble or something, it'll go along the flow of this vector field. Does that make sense? So the determinant is the rate at which an object flows through the vector field. I know I just threw a whole lot of physics at you, but just roll with me. Basically, if you think about like a river, so you got this river, and you have this little boat in it. Excuse my drawing, but you got a little boat on the river. If bar actually paddling or anything, it's just going to go along the current of the river, won't it? So your determinant basically calculates the rate at which you are being pulled by the flow of the river. Okay, we will get to more of vectors, vector fields, and stuff. Well, maybe not hit vector fields, but that's what it does. Okay, it's not arbitrary. It's not pulled out of thin air. It actually has some kind of important meaning. Now, define the determinant of a matrix, because matrices, by the way, I don't know if you noticed, but matrices represent vector fields extremely well. So to find a determinant is really, really easy. So finding the determinant is real, like I said, is really easy. Let's say that we have this matrix A, and this matrix A has the components A, B, C, and D. Okay, it's got the components A, B, C, and D. Another way we could think about these components, you don't have to necessarily write this down, but this is A11, A12, A21, A22. In other words, this is just talking about where in the matrix these components are. Does that kind of make sense? So remember, it's still row, column, row, column, row, column. So this is the second row, first column, second row, second column. Does that make sense? So if I want to find the determinant of A, the determinant of A is merely just A times D minus B times C. In other words, it's the diagonals subtracted from each other. Okay, so the determinant of this matrix A is AD minus BC. Okay, and I'm sure we talked about that probably in algebra 2, right? A little bit when you hit matrices, it's kind of the same thing. Determinant is AD minus BC. It's really that simple. So let's say that we have matrix B 3, 5, and I want to find the determinant of B, which shouldn't be too hard. And oh, let me also mention, you can only find determinant of square matrices. So I should have put that out there. All right, so we got the determinant of B would be 5 minus 12, right? Because it'd be 1 times 5, which is 5, 4 times 3, which is 12. So the determinant of B would be negative 7. That makes sense? Okay, let's do another one. Let's say you have C. Let's say this is another 2 by 2 matrix. Oh no, negative 1, 3, 2, negative 4 or something. So the determinant of C would be just negative 1 times negative 4 minus 3 times 2. So 4 minus 6 or negative 2. So computing determinants are really not that bad, right? Now, if we want to find the inverse of a matrix, all right, so we're just shifting gears a little bit, but still using determinants. If we want to find the inverse of a matrix, remember an inverse, technically, here's the technical definition of an inverse. It undoes, when multiplied, it gets back to the identity. So like 2 times 1/2 gets you back to 1, right? For example, these are inverses of each other, right? Because this is basically multiplication versus division of the same thing. These are inverses of each other. E to the x, ln of e to the x is 1 because these are inverses of each other, okay? Now, 1 is the identity, is the multiplicative identity, and that's what we want to get back to. In matrices, what you're trying to get back to is this matrix. This is called the identity matrix. It has a specific denotation of I. This is what we call the identity matrix. For a 3 by 3 matrix, that identity looks like this. So these are identities. Basically, think of this as this matrix represents the number 1 in natural numbers. Does that kind of make sense? It's the identity. Okay. And if I multiply a matrix by its inverse, I get the identity. And I'm going to prove that in a minute. So how do we find the inverse of a matrix? How do we find the inverse of a matrix? So here's what you do. Basically, if you have matrix A, we'll go back to matrix A is A, B, C, D. Then A inverse equals 1 over the determinant of A times D negative B negative C A. You can write that down. You're going to need that. Okay? And we'll go through this. So let's say that we have the matrix, just the regular 1, 2, 3, 4 matrix. I could have picked something better, but yeah, it is what it is. All right. Let's see. So to find B inverse, it's going to be 1 over. The determinant is going to be, remember, it's going to be 1 times 4 minus 3 times 2. So 4 minus 2, or 4 minus 6 is negative 2 times, and then you're going to rearrange these. So it's going to be 4, 1, negative 2, negative 3. And basically, I'm just literally doing what I did here. These two change places, and these two become negative. Everybody cool with that? So I multiply this out. So B inverse is equal to, now, when I multiply what we call a matrix, or multiply these by, this is called a scalar. It's just a number. Scalar is just a number. It's like a coefficient, okay? And whenever I multiply a matrix by a scalar, I'm just going to multiply this by all 4 of the terms. Does that make sense? So negative 1/2 times 4, that's going to be -2. Negative 1/2 times 2 is going to be +1. Negative 1/2 times -3 is going to be 3/2. And negative 1/2 times 1 is going to be -1/2. All I did, once again, was multiply this -1/2 by all 4 terms. Everybody follow me so far? Now let's prove that this indeed is the inverse matrix. And we do that by multiplying it by the original matrix, and you should receive the identity. So let's see. Let's see if we get it. So let's see. B inverse. I sure hope this works, because it'll be messed up if it doesn't. So we got 1, 2, 3, 4. We're going to multiply it by -2, 1, 3/2, -1/2. And I'm going to go one at a time and take it real slow, because I want to make sure that I absolutely get it right. All right, so this first one we've got, so for basically A1, which would be this slot like right here, we would have 1, -2, plus 2 times +3/2. This gives us -2 plus 3, because the 2's cancel here. So you have +1. So the first one's +1. Boom. The next one, A21, which would be this slot right here, is going to be -3 times -2 plus 4 times 3/2. This gives you, let's see, -6 plus 4 divided by 2 is 2. Okay, 4 divided by 2 is 2. 2 times 3 is 6. So -6 plus 6 is 0. So 0 goes right there. For the other ones, we've got A21, or A12 rather. You got 1 times 1 is 1, plus 2 times -1/2 is going to be -1, so that's 0. And then 3 times 1 for this last one, so for A22, the last one, we got 3 times 1 is 3. And then 4 times -1/2 is going to be -2. 3 minus 2 is 1. Oh, would you look at that? It's the identity matrix. So they are indeed inverses.